the scalar product or dot product of two vectors, because now we want to express work done in another way with another equation. It is the dot product of force and displacement. Work done is the dot product of force and displacement. So here we have studied addition of vectors last chapter. We have studied addition and subtraction of vectors. But in this chapter, we have to study the product of vectors. Two vectors are multiplied. There are two types of products. Scalar product and vector product are there. That means when two vectors are multiplied, some cases we get scalar product. That means that multiplied quantity. That means the work done is the dot product of two vectors, force and displacement. Force is a vector quantity, displacement is a vector quantity. When its dot product is taken, it is a scalar quantity. That means work done is a scalar quantity. But there are certain cases in which when two vectors are multiplied, we get another vector quantity that we will study in the next chapter. Okay. So here we are studying the dot product of two vectors. It is also termed as scalar product. Scalar, that means product is a scalar quantity. Two vectors are multiplied and that product is found to be a scalar quantity. So don't think when two vectors are multiplied it will be a vector quantity. Don't think like that. When two vectors are multiplied, some cases we get a scalar quantity, some cases we get a vector quantity. So this chapter we study work done is the dot product or scalar product of two vectors. Which are the two vectors? Force and displacement. And before entering into that part, we should know what is meant by dot product of two vectors or scalar product. Another name is scalar product, that we should know. For that, we can see two vectors. I will show the figure. See, these are the two vectors, vector A and vector B. And they are inclined at an angle. So these vectors are acting at this point O, and they make an angle theta between them. So what we have seen here, two vectors, vector A and vector B, two vector quantities. And angle, smaller angle between them, bigger angle, which is bigger angle. This one is the bigger angle. So we need only the smaller angle. So to consider two vectors, vector A and B, there may be different quantities, for example, force, displacement, like that, different vectors, and the angle between them is theta. Then the dot product, what is meant by dot product? Dot product, A dot B, it is a red like that, A dot. Which one? This one? Figure?
It is the dot product. Work is the dot product of.
That I am going to tell only after discussing this, okay? That I will tell you. After discussing this, we will go into that detail, okay? Okay, now you listen this.
Okay.
So here you can see two vectors, vector A and vector B, and they are inclined at an angle theta. That's a smaller angle between them is theta. Then A dot B, this is red like dot, a dot is put here now, so it can be read like that. A vector A dot B is equal to AB cos theta. What is A? It is the magnitude of this vector, magnitude only. We are not putting the vector sign here. See, so A is the magnitude of vector A, and what is B? B is the magnitude of vector B. And what is theta? Theta is the smaller angle between the two vectors. So what is A dot B now? A B cos theta. Where what is A and B? A and B are the magnitude of the two vectors. And what is theta? Theta is the smaller angle between the two vectors. So now you got the equation A dot B equal to AB cos theta. And you have to tell each term what it represents. A is the magnitude of vector A, B is the magnitude of vector B, and theta is the smaller angle between them. So A dot B equal to AB cos theta. And here A is a magnitude. It is not a vector. B is also magnitude. It is also not a vector. Theta is not at all a vector. So all these are scalar quantities. A, B, cos theta. All are scalar quantities. You see, when we took the product of two vectors, we got a scalar quantity. See, Now, all these are scalar quantity, A, B, theta, cos theta. So everything are scalar quantities. So what we got, dot product of two vector is a scalar quantity. That's why it is called scalar product. It is also called scalar product because all the quantities we got by finding the dot product are scalar quantities. So it is also named as scalar product. Okay, and there is some other way of explaining this that I'll explain here. Geometrical interpretation of dot product of two vectors. Geometrical interpretation, you can see. Rituparna is waiting. Many are not showing not signed in like that. Why? That's why it is showing absent in and tab. You have to sign in and enter. Okay. So geometrical interpretation of dot product of two vectors. Vector A dot B, we just now studied AB cos theta, or it can also be written as BA cos theta. So A into B cos theta, it is written in bracket. Similarly, okay. What?
The slide is blank.
Blank? No, nothing. See?
No.
Everybody
No,
is,
ma'am,
you are seeing? Krishna Sri?
Yes,
ma'am.
Okay.
yes,
So,
ma'am.
We can see, ma'am.
okay.
No problem.
Okay. Maharnisa, it may be due to net problem. I will share the video. Okay, you can see it later if you find it difficult. Okay. So A dot B equal to AB cos theta, A into B cos theta. So in the figure, you can see last figure. You see, in this figure, you see here this is vector A and vector B. We draw a perpendicular to this axis. That means OP direction. That means vector A's direction. From vector B, you draw a perpendicular. Then that will be the component of vector B. We have studied resolution of vector into rectangular components. When we resolve vector B into rectangular component, one component we get here and one component we get along the y-axis. That is B sin theta. And nearby component that will be cos component. So this is B cos theta. This component of vector B in the direction of vector A is B cos theta. So we can also explain like this. See, magnitude of vector A into component of vector B in the direction of A. Like that we can explain. This also can be explained in that manner. That is magnitude of vector A and component of vector B in the direction of vector A. Like that. Similarly, here you see this diagram. So here I have drawn perpendicular to this in the direction OQ. So from A we have drawn the perpendicular. This is 90 degrees. From dotted line is showing the perpendicular drawn. So from P you have drawn a perpendicular to the vector which is vector B. From A you have drawn perpendicular to this vector B. And this is this component, that means OS, up to OS, it is the component of vector A in the direction of vector B. So we can also explain in that manner. That means magnitude of vector B into component of vector A in the direction of B, like that. So magnitude of vector B. Component of vector A in the direction of vector B, that is A cos theta, B A cos theta. So B A cos theta. So that is the geometrical interpretation of the dot product of the vectors. Muhammad Adil coming now only. Now that all reached now. What time? 20. Next problem, I don't know. It's 10:20 now. Now only reached. So we can express the geometrical interpretation of product of two vectors. A dot B can also be written as A into B cos theta or B into A cos theta. So dot product of two vectors is also defined as product of magnitude of one vector and the magnitude of the component of the other vector in the direction of first vector. So what we can say, what is the geometrical interpretation of dot product? Dot product of two vector is defined as product of the product of magnitude of vector A and component of the magnitude of the component of the other vector in the direction of the vector A. So it is defined as the product of magnitude of one vector and magnitude of the component of the other vector in the direction of first vector. Understand? So that is another way of expressing the dot product. So what is A dot B now? What do you know about A dot B? A dot B, vector A dot vector B, dot product of two vector is a scalar quantity. What is the magnitude we are getting? We are getting AB cos theta. What is A and B? A and B are the magnitude of two vectors. What is theta? Theta is the angle between the two vectors. Smaller angle between the two vectors. Okay, in special cases we can discuss. When two vectors are parallel, then theta equal to 0. See, for example, we have taken unit vector I dot I. For example, I means it is the unit vector along the x direction. You see, I is the unit vector along x-axis, j is the unit vector along y-axis, and k cap is the unit vector along z direction. Then I dot I, what is the meaning of I dot I? I dot I, same, see, both are in the same direction. I dot I. I dot I, what is the magnitude of I cap? 1. 1 into cos 0. 0 is the angle between I and I. I is the unit vector along x direction. So I dot I is equal to 1. Similarly, what is j dot j? But first you have to write magnitude 1. Again magnitude 1. 1 into cos 0. 0 is the angle between j dot j. Same vector. Theta will be 0. Same vector. Angle between j dot j, that is equal to 0. So j dot j is equal to 1. Similarly, k dot k is equal to 1. So for unit vectors, I dot I equal to j dot j equal to k dot k equal to 1. So we can write when theta equal to 0, when two vectors are parallel, then theta equal to 0, cos 0 equal to 1. So what is A dot P? AB cos 0 equal to AB into 1 equal to AB. And for unit vectors, because their magnitudes are 1, so you get I dot I, j dot j, k dot k equal to 1. But if they are having the magnitude, it will be, for example, A dot B equal to AB when they are parallel. When two vectors are parallel, A dot B equal to AB. For unit vectors, it is 1. When two vectors are perpendicular, what happens? When two vectors are perpendicular, theta equal to 90 degree. So cos 90 becomes 0. Therefore, A dot B equal to AB cos 90, that becomes 0. It means dot product of two perpendicular vector is 0. When two vectors are perpendicular, dot product is 0. And for unit vectors, see, you can see unit vectors, they are mutually perpendicular. So I dot j, 1 into cos 90, 1 into cos 90, cos 90 is 0. So 1 into 0, that becomes 0. So vectors are perpendicular, their dot product is 0. For unit vector also it is 0. Understand? Properties. Next we have to study properties of two vectors. Dot product or scalar product of two vector is obey commutative law. That means A dot B. What is A dot B? AB cos theta. What is B dot A? BA cos theta. So what we can write? A dot B equal to B dot A. So that is one property. So question may come, what are the properties of dot product of vectors? So you can study these properties. It obey commutative law. A dot B equal to B dot A. Next you can see dot product is obey distributive law also. Is obey distributive law. A dot vector A dot B plus C. Vector B plus vector C equal to, see, first you have to multiply this one, A dot B plus A dot C. So that is also another property of a dot product. First property, obey commutative law, dot B equal to B dot A. Second property, obey distributive law. Vector A dot vector B plus vector C equal to vector A dot B plus vector A dot C. So properties, next property. Yes. Next, yes, next one, work done. Work done is the dot product of two vectors. Work done is the dot product of two vectors. And before that one page, page 3. This is 3. Page 3 is, let me see, okay, I'll explain with this figure. So you can see here, force, this is force, and this is displacement. See, you can see two blocks here, two blocks. One block is here kept here, and we apply force. For example, a lawn roller. You can consider lawn roller. You have seen. Yeah, in that we apply force in this manner. So the inclined way only we apply the force, and the roller will move horizontally. We apply force in an inclined way. The roller will move horizontally. So this displacement will be along the horizontal direction, and force is inclined. They are making an angle theta. They are making an angle theta between the displacement is a vector quantity, force is also a vector quantity. And here see, work done. How will you calculate the work done in that case? Here the displacement and force are not in the same direction. So when they are inclined at an angle, we have to find the dot product of this force and displacement. Both are vector quantities. So work done is equal to F dot S. F dot S. And you can see, as we have done in the geometrical interpretation, we have taken the component of force in the direction of displacement by drawing a perpendicular. So from F, we have drawn a perpendicular to the displacement vector. Then up to this, from this point to this, that will be the component of force in the direction of displacement, F cos theta. It is written as F cos theta. F, where will be F sin theta? It will be here. It will have no effect when we find the dot product. So component of vector in the direction of displacement, that is only useful. Other component is not useful. F sin theta is not useful here. Component of vector F in the direction of displacement, that is used here to find the work done. So work done is the dot product of F dot F and S. Work done is the dot product of vector F and vector S. And what is its magnitude? Magnitude is Fs cos theta, or in geometry, the geometrical interpretation is the product of the displacement, magnitude of displacement, and the magnitude of vector F in the direction of displacement vector, in the direction of displacement. F cos theta. What is F cos theta? Component of vector F in the direction of displacement. Is it a scalar or vector, F cos theta? It is a scalar quantity because F is the magnitude of that vector. Cos theta is the cosine of the angle theta between the two vectors. So F cos theta is a scalar quantity. S, magnitude of vector S, that is also a scalar quantity. So F cos theta into S all together is a scalar quantity. So what is F dot S? Fs cos theta. And what is the geometrical interpretation of scalar product of F and S? It is the product of magnitude of displacement vector and the magnitude of component of vector F in the direction of displacement vector. What is F cos theta? Component of vector F component of vector F in the direction of displacement. Okay. What is F cos theta? Component of vector F in the direction of displacement. What is S? Magnitude of displacement. Okay. The work done, we got the formula now. For that, we studied the dot product and all. Work is a scalar. You see, we are not at all putting the arrow mark here. We are not putting arrow mark here. It is a scalar quantity. Work done is a scalar quantity, but it is the dot product of two vectors. Two vectors, dot product is work done. So that is a scalar quantity. So we don't put arrow mark for work done. Work done is a scalar quantity. Work done W equal to F dot S. Vector F dot vector S. SI unit of work is joule. And now this is the diagram for that. So we got the formula for work done by a, this is the formula for work done by a constant force. Varying force, we cannot use this formula. If force is varying, when we apply constant force, then only we can use this formula F dot S, Fs cos theta. If the force all the time, if it is varying, every instant, if the force is varying, you cannot use that. Why 39 is showing in your class trunk? 39 are there. Aisha joined just now. Okay. Nature of work. Work can be positive, negative, and zero. How is it? How is it? Let us explain with the equation. See, work done is equal to F dot S equal to Fs cos theta. When is this work done positive? When theta is acute angle. When theta is acute angle, so cos theta will be positive, hence work done is positive. And some examples are given. When a body falls freely under gravity, when a body falls freely under gravity, force is downwards, gravitational force is downwards, and motion is downwards, displacement is downwards. So force downwards, gravitational force downwards, displacement of the body downwards, both are in the same direction, but so theta equal to 0. So therefore, work done by gravity on the body falling freely is positive. Work cos 0, 1. Understand? So that is a positive quantity. Work done is positive. Both displacement and force are in the same direction. Work done is positive. Another example. When a lawn roller is pulled by applying a force along the handle at an acute angle, work done by the applied force is positive. Acute angle, that case is what we have seen like this. Force is applied in this direction, displacement takes place in this direction, and here the angle is acute, therefore work done is positive. Can you tell one example? Anyone? Can you tell one example for work done, positive work done? Anyone? Tell one example, I'll ask. Midun, can you tell example for positive work done? Another example, two example here I have given. Another example. Both should be in the same direction. Force and displacement should be in the same direction. That's all. Can you tell? All are present here, so you cannot keep quiet there. You can tell at least. If you don't know tell. Midun, can you tell? No. Then I'll ask to Alok. 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 No. And then Megha Rajesh, can you tell? Megha Rajesh. Both in the same direction. Very easy question I am asking. One example for work done positive. Force and displacement should be in the same direction. Tell one example. Megha. Megha also. Eh? What? Both in the same direction. You can't hear?
Teacher, I
Ah,
didn't understand. Kattila.
Kattile. Okay. Okay, I'll explain.
Teacher, when stone is thrown from
Stone is thrown
the top of the
top of a
tower to the
Ah.
ground.
Then we work done by what is positive? Work done by gravity. Work done by gravity, positive. But another example. That example I have given here. When a body falls freely under gravity, the body is falling downwards. That is displacement is downwards. Gravity is also downwards. Earth is attracting all bodies towards its center. Force is downwards. Displacement downwards. Another example I am asking. Same example. This is same example. Another example. Tell me. Who will tell?
Ma'am, when a body is moving in a horizontal path,
When we apply horizontal path,
and we apply force.
when we apply force.
When a
Okay, correct.
force is ma'am.
Okay, correct answer. So when we apply a force and the body also move in the same direction, for example, a table, we exert force on that table to move it towards east, for example, towards east. We are applying a force, and body moves towards east, and we are applying force towards east. Both are in the same direction. So work done by us is positive. Work done by us is positive. We are doing a positive work. Understand? That is then positive work done. Okay. And can you tell another example? When we exert a force to throw a body upwards, I will ask question. I am exerting a force to throw a body upwards. What is the work done by me? I am applying a force to throw the body upwards, and a body is moving upwards. Is the work done positive or negative? That is the question. Answer. Ria, can you tell what is the answer? Positive or negative? Work done by me. I have applied the force to move the body upwards. Body moved upwards. Is the work done positive? Ria. Nobody is answering. Who will tell?
Teacher, ടീച്ചർ ഈ അപ്വേർഡ്സ് ചെയ്യുന്ന ഗ്രാവിറ്റിയുടെ റിവേഴ്സ് ആയിട്ടല്ലേ അറിയുന്ന
അപ്പൊ വർക്ക് ഡൺ ബൈ ഗ്രാവിറ്റി നെഗറ്റീവ് ആണ്, മനസ്സിലായില്ലേ? ബട്ട് ഐ ആം ആസ്കിങ് വർക്ക് ഡൺ ബൈ മീ
Positive.
Correct. Krishnasri, work done by me is positive, but work done by gravity is
negative.
Correct. Like that you have to tell. Gravitational force is downwards, but body is moving upwards. Then work done by gravity is negative. Correct answer. But work done by me and the body moves upwards. Work done by me is positive. I have applied force upwards. Body also moved upwards. So work done by me is positive. But work done by gravity is negative. Okay, that's the difference. And another example, I'll see. I exerted a force to move the body towards east and telling the direction towards east. Okay, but body is moving east. Body is also moving towards east direction. So work done by me is
Positive.
Positive. What work done by frictional force? Can you tell? Work done by frictional force?
Negative.
Correct. Frictional force is always opposite to the motion. So displacement in one direction, frictional force opposite direction. So work done by frictional force is negative, but work done by me is positive. So that is the difference. So work can be positive, negative, and zero also. When this work done becomes zero, can you tell? Different cases are possible. According to this equation, W equal to Fs cos theta. Which all cases work done becomes zero? You can tell. From the equation you can tell. What all cases work done becomes zero? Tell. One by one, you can tell. Who get the answer first, you can tell. Huh? When is work done 0?
when the,
Huh?
when the body doesn't move, then we apply
Yes, correct. Jnanaprakash അല്ലേ പറഞ്ഞത്? Very good. When the body does not move, displacement 0, work done 0. See, for example, when we exert a force on the wall, when we exert a force on the wall to move it, it will not move, but we are applying force. So, work done is 0. Another case, tell. Only 5 minutes more. Another case, tell. Please tell fast. Work done 0. If we work F is 0, if we are not at all applying any force, no displacement, work done 0. Another case is that when theta is 90 degree, I will tell that. Theta is 90 degrees, 0 work done, you can see here. When force applied F and the displacement S both are 0, work done is 0. Again, when angle theta between F and S 90 degree, then also work done is 0 because cos 90 is 0. When we push hard against a wall, work done is 0 because displacement is 0. A weightlifter holding a 100 kilogram mass steadily on his shoulder for 30 seconds does no work. See, weightlifter is holding 100 kilogram mass steadily on his shoulder for 30 seconds. He is holding that block body. See, but work done by him is 0. Why? Because there is no displacement to him. So work done by him is 0. So the work done in the language of physics, it is different. See, when you study day and night, we tell, oh, so he is working hard. That is different. But if we are not having any displacement while applying the force, we are work done is 0. With this weightlifter, you see, he is holding the weight. See, 100 kilogram mass is holding for 30 seconds, but work done by him is 0. So in the language of physics, it is different, work done. For example, a coolie carrying a load on his head. In railway station, you can see porters, coolie carry, they will help us to carry the load, but we have to pay money for them, for carrying the load from that platform to the station, like bus stop, like that, to catch a taxi or like that. They will help us, but we have to pay for them. But in the language of physics, he is not doing work. He is carrying the load and walking along the platform horizontally, angle between load applied. When he carry load on his head, we have to apply force upwards. We have to apply force upwards to load, not to lift a stone. We have to apply force upwards. In order to carry a load on our head, we have to apply force upwards, because load is acting downward force and we have to exert an upward force on it. So we are applying a force upward, or that coolie is applying a force upward, and he is moving along the platform. So horizontally he is moving, force in upwards, and direction of motion along the horizontal direction 90 degree, angle between force and displacement is 90 degree. So work done by him is 0. So that doesn't mean that we don't have to pay for him because his work done is 0. But that is the difference in the common language and the physics language. Physics language, work done is 0. Coolie carrying a load on his head, walk on the horizontal platform, the angle between the force and displacement is 90. So work done is 0. Then another example. See, this is another example. A stone is rotated uniformly in a circle. In anti-clockwise direction, it is rotated. And we know for any body to keep in circular motion, we have to apply centripetal force towards the center. We have to apply centripetal force to keep the body moving in a circular path. And the displacement, how will you find the displacement? Displacement at a particular instant, that will be, it is anti-clockwise. So it will be, if you draw a small displacement, here small length you have to draw, small length. And direction is shown like this vector S. And vector F is towards the center. Force is acting towards the center. Displacement is along this direction. Angle between them is 90 degree. So work done is 0. F dot S, Fs cos theta, Fs cos 90, the work done is 0.